Hello, everyone. I put a bunch of logos here. I hope it doesn't make it look like a Formula One racer with all those logos. Some of those projects I've contributed to or I'm a big fan of. So today I'm going to talk about Iceberg and the Deconstructed database, and I've subtitled it The Advent of the Open Data Lake. So it should be interesting. So I've split this in three parts. First, I talk about what I mean by the deconstructed database and how Iceberg fits into it, a bit about why it is important, and then we'll go into the details of how we build a database from its components. So first, what's the deconstructed database? So if I go back a little bit of how does a query engine work, and you start from a query, but then there's a few steps on how the query goes from understanding to execution. And you start with, parsing, understanding the syntax of the query, and then semantics. So like understanding, what's a field, what's a table, what field is coming from what table, how those things relate to each other. And then you go into an optimization phase that will lead to what's the best plan to execute on the query engine, right? So you take your query, turns into a syntax tree, and then you retrieve metadata about those tables. We refer to, you optimize, you get a plan, right? And you go from, I have my query and I know that I need to read data, join it, and then I generate an output. And so in terms of what that deconstructed database means is we've been building components that are reusable and that you can build a database out of, right? So if you start from this front-end layer, when you have things like Substrate and Calcite, enabling producing a plan, optimizing it, and submitting it to a query engine, and then you have a query execution layer that will access to a storage layer, and Arrow is usually the format of choice for exchanging and processing data in memory through that, right? And OpenLineage come as a mechanism to ensure you know where data is coming from and going to, and have a governance layer, right? So those are the generic layers on more like front end, just preparing the plan to know what to execute, and more back end, how do we actually execute and splitting it into the actual, being able to do the joins, etc., and accessing data efficiently. And so the other thing that has been happening over the past 10 to 15 years is this notion of decoupling storage and compute, right? If you remember the Hadoop days, we're going to move processing to the nodes, right? So processing is close to storage, and we're going to access data fast instead of getting data out of the machines to process it. And actually what has been happening at the same time that Hadoop was growing is that network got a lot faster than, access inside a machine got, right? Like, so the speed up, the acceleration in networking and the evolution of the technology, network faster than the other side, right? It grew faster. And so we moved from this, compute and storage tied together, right? So if you used Vertica or Redshift back in the day, that was very much that way it worked, right? You would have a cluster and the storage was tied to your compute node, right? If you needed more storage, you needed to add more compute. If you didn't have enough compute, well, you had to buy more storage to go with it, right? So it created a whole bunch of friction and tension on how you make this work. And it was really inconvenient and creating tension. So now we moved, if you look at Snowflake, BigQuery, a lot of those technologies like Redshift is evolving as well in this direction into, well, now we can store the data in blob storage, separate the networking from the storage from compute, and be able to, you can have multiple warehouse coming in, accessing the same data. You remove the silos, you remove the constraints of, you can scale compute independently of storage, and it makes things a lot easier on how you store data and how you query it. And so that leads me to part of this deconstructed database layer idea, right? So I'm focusing on the storage layer in this talk, what is the right abstraction to access this data in this storage layer in the database, right? So there's two main things, right? One, on the distributed read access, right? If you want to be able to access this data in parallel, you want one, an efficient format for vectorization. So you'd be able to read it and process it effectively right off the bat, and being able to read it in parallel from multiple streams, right? You have this notion of, I need to be able to access it in parallel and in a format that I'll be able to process it very fast. And the other aspect is you don't want to pull all the data, right? You want to pull as little data as you can, which is what the notion of pushdowns comes in place, like projection. What are the columns I need? I don't read all the columns. I read only the ones I need. What are the filters? I read only the rows I need from those tables. And potentially pushing limits. Obviously, if you're going to have a limit in your SQL query, you don't want to read more rows than you need that you're going to throw away later. And possibly you can push down even aggregations in the storage layer to materialize as little data as you can and read less data from that storage layer before you do other things like joins that require looking across different stores. And so those are the key parameters, the key abstraction we need from that storage layer. So now if we look at the options you have for abstracting the storage layer, we really have two options, right? So there's two levels of abstraction. On one, there's Iceberg and a file format. So typically it's Iceberg and Parquet, where you have this columnar format inside the table abstraction that Iceberg provides. So that's kind of the standard open data lake implementation. It is great for bulk updated, scalable, and cheap storage, right? Like, so Iceberg works well when you're going to do bulk update, where you insert a bunch of data at a time or you update a bunch of data at a time. And it scales really well, and it's cheap because it's S3, and it's great in that environment. And there's no need to operate any storage layer, right? Like, it's S3. S3 is magical. It just scales. It's just like, you don't have to do anything in that environment, right? It's just cloud-based. You forget that there are servers somewhere underneath. The other one is Aeroflight. So Aeroflight enables a finer grain implementation of a storage layer. You can build your own storage. And in particular, you'd want to do this if you want to do something that has lower latency, right? On the Iceberg side, we talk about you do bulk updates. If you implement your own service for the storage layer, using Aeroflight, for example, then you may be caring about low latency ingest. Like, maybe you make the storage layer transactional, or you want to have data available as soon as it's accepted, or things like that. So it creates a lot of flexibility and a lot of power, but it comes at the cost of, there is a service you need to maintain that needs to be elastic and so on, right? Like when in the case of Iceberg, where the service is S3. So if you look how this works, if we look at Aeroflight, you will have an execution engine that potentially is distributed and that will read in parallel for a flight service that will expose this distributed collection of data, and will exchange it as arrow format that would enable the execution engine to process this data very fast, because it's in a format that's amenable to vectorization and a fast processing. On the other hand, in the Iceberg provides an abstraction that is very different, right? Like, some of the attributes of Iceberg compared to using the proprietary storage of various systems, right? When you think of BigQuery or Snowflake, they do store your data in blob storage, right? Like, whether it's GCS or S3, they do already store your data in blob storage, and they use those properties of, oh, we can do bulk update and it's going to be cheap and so on. But when you use Iceberg, you own your own data, right? Instead of usage going against your provider's bill, and then, they decide what margin or come an advantage if you use Snowflake, for example. Instead, you own your data, it's on your bill, and you decide how you integrate it, what other tools you have the flexibility of using other tools. And it gives you a proper table abstraction as opposed to, storing files in blob storage. You have an actual thing that looks like a data warehouse from the abstraction layer and makes it a lot easier to maintain and gives better abstraction to correctly updating this data. And it's scalable, it's cheap, and because it's blob storage. And so in the execution engine, on the storage layer, you still have many machines serving it, right? But you don't have to think about it. It's S3, it's almost infinitely scalable. You don't have to think about it. And all that aspect of how you scale it, how you scale access to it, all of that is taken care of, right? And then instead of arrow being exchanged, what is going to be exchanged on the wire is either Iceberg metadata that describe what snapshots you have, what are the various versions of the table, and column chunks, right? Like when you access columnar data, you're accessing a subset of the files, which are just the subset you care about, right? Which is the idea of being able to do the push downs and reading only the data you need. And so when I talk about a proper table abstraction for Iceberg, it's one, it gives you snapshot isolation, right? When you update data, you don't have to worry about, while I'm adding data in the table, someone else that is reading this table at the moment is going to see it. No, people see whatever the latest snapshot was when they started reading. They don't have to worry about you updating the table when you're reading it. So you have this snapshot isolation that helps you create consistency, allow you to roll back right into a table. There's a partitioning abstraction. So you don't have, like back in the day when we do incremental processing, you would create partition with folder, year, month, day, hour, right? And put files in there and tie hard coupling, your scheduling, and the partitioning of the data. Now it's not a problem anymore because you abstract that out and you can decouple this partitioning, you can change the partitioning, you can optimize your storage without having to worry to impact all the application logic on top of it. And it helps implementing those efficient push downs, projection, filter, limit, all understanding the schema, the evolution of the schema, and taking advantage of the underlying columnar storage. So that's kind of an overview of how Iceberg fits in that. And why is it important? So back in the day when you were building a database, you had two options, right? So one, you could use an existing database, you could use a proprietary Oracle, and if you needed to scale, there was Oracle Rack that cost a lot of money and give you a transactional distributed system, or open source with MySQL, Postgres, right? So either you use something or you build something from scratch, right? And that's what happened with Hive, with Presto, and you build everything from the ground up. And I wanted to give the example of Hive, of what it takes to do this, right? So we take Hive. When Hive was created, the execution engine of choice was Hadoop, right? You have Hadoop MapReduce. MapReduce is great for looking for a needle in a haystack, right? Like you have this giant haystack, you have petabytes, if not more, of data. At the time it was petabytes, now it's like exabytes. And you have a lot of throughput to find it. But it's kind of akin to finding a needle in a haystack with no plows, right? It's a very blunt tool, puts a lot of power into scanning everything and finding the thing. But it is composable, right? MapReduce is very composable. You can build complex system. And the initial version of Hive was just that. You take a SQL parser, you take the plan, you turn that into a physical plan of MapReduce jobs, and you can actually implement SQL, right? And that was the first version was, right? So you can create this plan, scan everything, do a join, and so on with MapReduce. And it took a lot of effort to get from there to actually have a performance, latency, interesting query engine that does all the things you need to have an actual query engine that is usable in this context, right? So you need an optimizer so you can pick the best plan and take advantage of the push downs in the storage layer. You need a shuffled service that, like MapReduce, is very towards doing very high throughput, persistent evolution, right? It snapshots the data in between every steps to disk to make sure it can restart from where it stopped, right? But makes it very expensive. So you can have a shuffled service that have different characteristics depending on what you're doing. You want to have things that are more or less reliable, and you replay in different way, and you need fast interchange. You need a columnar storage as an efficient storage layer and enable quick access for your OLAP queries. And you need vectorization, like rewrite the entire execution so it can be efficient and fast and ensure low latency latency on execution. So this is all like an example of all the work that has been done for a decade plus, adding into the project to what it takes to actually build one of those from scratch. So how to build one in practice now, right? So we talked about generally what it looks like. We talked about why it's important, because it's either you reuse something, but you're kind of stuck with how it works, or you build ones from scratch, but it's an enormous endeavor. So what changed along the way? Or how do we do things differently now, right? So the first thing to think about is, what are your trade-offs, right? What's the volume? Does it fit on one machine? Does it fit in memory on disk? Does it need a distributed system, right? If you look at things like DuckDB has a very different architecture from Presto, say, right? Like Presto is designed for distributed. DuckDB is designed for taking advantage of the parallelism of a single machines. Now that machines have a lot more processors, have a lot more memory, they have SSDs and so on. And so it takes advantage. It's written in a different way to take advantage of the different trade-off you take of the different ratio of speed of accessing the data versus parallelism, as opposed to a distributed system. Second, you can think about latency. Do I care about real time, being able to query the data as soon as it's written, right? Do I need a read or write semantics, or is bulk ingest and adding latency between ingestion and processing sufficient? And precision, right? The other things when you can gain performance is, can we use approximate data structure for aggregation? Can we do sampling and make things faster? And so in this idea, now, I started with this deconstructed database, where it's like, how we rebuild the database, right? We took the database and we split component out and deconstructed it and make these composable and reusable. How do we rebuild things together? So I go back to this picture, right? Oh, now I'm thinking about, okay, we have the layer, the front end, right? How do we do the query parsing, the optimization? How does that get pluggable? How do I have a query execution? And how do I think about the storage, right? So I'll talk a bit about the thing that were needed to build for Hive being one example, and how we use that in general. And a lot of different systems have reused that general idea, right? So first, when you think about the optimizer, there are two different levels of how that works, right? So you parse the query, and then you can start, there's a whole bunch of rules that are obvious, right? That get applied all the way. For example, we look at this select that was doing a join and filtering on something. You always want the filter to go all the way closer to the scan of the data before the join, right? Obviously, you don't do the join first, and then you filter out the rows you don't need. You filter out the rows you don't need before you do the join, and then you do the join. It's always more efficient. And so some of those are rule-based, they always happen. And then there are a whole bunch of things that are cost-based. You need a cost-based analysis because it depends a lot on the shape of the data, the distribution of keys and so on, what's going to work better, and the size of the data. And so join ordering is a great example of things that it depends a lot what is the best way to do things. And calcite is usually the main project that you can use that has been integrating like 20 years worth of experience in the optimizer sense, and that's been used in a lot of projects, including Hive, right? Hive, when it started needing to go faster, adopted calcite. On the vectorization side of things, so I talked about how we need vectorized execution to go fast, right? So this came from this MonadDB X100 paper talking about how to make things faster on modern processors. So modern processors don't just execute operation one after the other. They kind of stagger them, or they start the next instruction before the next one, the previous one is finished. So it's actually very valuable to be able to execute things on columns, right? And there are a bunch of reasons. I'm going fast on there because it's kind of more of a high-level presentation, but optimizing for the pipelining of the processor, for the cache locality in the processor, and making sure that is going to go as fast as it can, you need to lay out data in columns, in memory, in vectors, so that you can enable vectorized execution. And this last world, Arrow has been the project that standardizes how you represent this data in columns, and how it can be exchanged very cheaply on the wire, either between a storage layer and the execution layer, or within the execution layer between operators. And data fusion that came out of Arrow is an implementation of a vectorized execution that enables things going fast. So today, if you build a query engine, you probably use Calcite, you probably use Arrow, you probably use data fusion, and you can connect those things together in between things. Right? A little this, I think we all use Hive Metastore, not because that was the greatest thing, but because that was the only thing, right? That was what existed. And the Hive Metastore started from this little, I need somewhere to know where my table exists so I can build this SQL abstraction on top of MapReduce. And it kind of grew organically, like in the ecosystem. And I think now with Iceberg, we have a REST API that kind of like from scratch, okay, what do I actually need? Let's build an API from this new abstraction of this notion of open data lake and this shared storage that can be used from different systems. And open lineage is the other aspect of data. I alluded to it in the early slide, is once you start processing data and reading and writing data, you need to understand how the data flows in your system. Open lineage is this abstraction that you can connect to your data catalog, your governance, your tool of governance of choice, and so on, to build a graph and understand where data is going, where it's coming from. Can I guarantee quality? Can I guarantee that I'm not going to break GDPR and get fined, and so on, right? So that's kind of the other aspect that you plug to enable connecting this to the other system. So if we think of this open data lake notion that Iceberg is the key building block of, you want to have this notion when you centralize where your data is stored. But centralizing your data means you need to have the catalog and you need to have governance. You need to understand how those tables have been produced, right? Like the key part of this data storage is having more metadata about the tables, understanding how they get built, the lineage, the governance, who owns what, and so on. That's kind of the centralized aspect and a lot of what Iceberg provides. And I think on lineage, maybe more a little open lineage. And then there's a specialized part that you can have multiple of, is the compute engine, right? You have your shared storage and you have governance around your data. How do I own it? Who owns what in my organization? And then I can plug it into Snowflake, BigQuery, Trino, Spark, and Dremio, others. And there, I didn't have enough space on my slide. But, and that doesn't matter. If you want to try something new, you can easily try something new because your data is not buried inside one vendor, right? And you own your data and you can decide what to do with it. And you have flexibility, and maybe this needs to be processed in Spark now, but actually we want to process it in BigQuery or something else, right? So there's kind of this notion of how Iceberg provide this open data lake in this deconstructed database, right? Like we're taking out the storage layer and but we do this in a way that is very efficient and that makes sense, and how we build all those things around it. So that's it. That's the kind of general conclusion of how Iceberg answers a lot of those questions. Thank you very much.